Alright. So this is unit 5, which is conic sections, and as we discussed in the last class, all these sections, be it circle, be it parabola, be it hyperbola, be it ellipse, all these are part of a conic section. What do we mean by that is that if you have a cone and if you dissect or cut it with a plane, this is what you will get. Alright. So let's say this is a cone, and if you use a plane, let's say this is your plane which cuts this one, and then when you look at whatever you got by cutting this from this side, this is the shape that you get, which is nothing but your parabola. And similarly, if you cut along the horizontal axis, and then when you look at what did you get by cutting it with this plane, you get nothing but a circle. When you look at it from the top, this portion, when you cut the, hey Chris.
Hello.
So basically, we're just doing a quick recap of what we learned in the previous class, and then we'll continue from there. So all the, as part of this chapter, conic section, primarily these are all the different shapes that you get by cutting a cone using a plane, be it horizontal, be it a slanted one, be it by cutting it vertically. So if you look at a parabola, that's part of a conic section. That's by cutting a cone. If you look at a circle, that is also coming by cutting a cone with a horizontal plane. If you cut this in a slanted way, then the shape that you will get, right, is nothing but your ellipse. Similarly, if you have two cones sitting on top of each other, and then when you, let's say, use a plane for cutting it, then if you look at what you will get, it will be like, this is nothing but your hyperbola. So that was the understanding that we built in the previous class. Is everybody clear with respect to why we call them conic section? Primarily a question for Prisha and Dhanusri, who were not in the previous class, that's why I'm asking that. Yeah? Now, so when you look at all these unique, what do you call, unique shapes, like be it circle, be it a parabola, be it a hyperbola, be it an ellipse, all these are coming from the cones. When you cut the cone with different planes, the other things that you get. So that essentially means there are a lot of things common among them. Everything that you look at, right, be it a parabola, there is a center for this one, around which it revolves. If you look at a circle, it revolves around the center again. If you look at an ellipse, that also has something which is called the center of this one. In case of ellipse, we say this is major axis, this is minor axis. So where it is broader, it's major axis, and this is the minor axis. Similarly, when you look at hyperbola also, this also has, unique thing about hyperbola is its center is outside, because one part of the hyperbola is on one side of it, other part of the hyperbola is on the other side of it, but there's some symmetry around this one. So these are the correlation that we have with respect to all the different conic sections that we will talk about. So that being said, you all are aware of the standard form of an equation for a circle, right? Which is x squared plus y squared equal to r squared, or if I go with a more generic definition of that, it is x minus h squared plus y minus k squared is equal to r squared. Correct? Where h and k are the coordinates of the center. So if this is a circle, this is h and k, these are the coordinates of this one, and this r is nothing but your radius. Everybody is clear with this, correct? This is a standard form of the circle equation. Yeah? Risha, Dhanusri, Dev, everybody? Yeah. Now, so this becomes our guiding principle for all the shapes or all the unique shapes that we'll talk with respect to conic section. So we'll take this as a base. Now if you look at this, if you convert this into, let's say, if you relate this as a unit circle, then your equation becomes x square plus y square equal to 1 square, where 1 is your radius. When we say unit circle, we are essentially talking about a circle which has radius equal to 1. So these are the correlations. Now let's look at, for now we will assume that our center of the circle is the origin of the coordinate plane, meaning 0, 0. So in that case, the circle equation would be x square plus y square equal to r square. Correct? Now, what we learned about in the previous class was, if you look at ellipse, it is a squeezed form of a circle. If you guys would have played with the toys where it's more of a cushy thing, right? Where you squeeze it from the top. If you squeeze it from the top, it becomes like an egg. A form similar to an egg, right? This is your nothing but ellipse. And the property that we talked about was that when you look at ellipse, it has a center, and then this is called the major axis and this is called the minor axis, meaning where this is broader, that is called the major axis, where it is thinner, that's your major axis. So that's why it's called, this is called the major radius, or we will give it a name like A, and this is the minor radius, which will give it a name as a B. Or in a more generic term, you will say A is your radius along the x-axis and B is your radius along the y-axis. So when you relate that with the generic formula for the circle that or the standard formula for the circle that we know, when the origin is origin and the center are the same, meaning h and k are 0 and 0, then you can again use the similar this thing to find out the equation for the ellipse. Here the good thing is you don't have one common radius. In case of a circle, you had one radius which is covering the entire 360 degree of the circle. Wherein here you have two flavors of the radius, one which is along the horizontal axis, one is along the vertical axis. So that is where this gets replaced with a square and this gets replaced with a b square. So now if you look at it, this is x square by a square, meaning this becomes a standard form of the equation for an ellipse, where a is nothing but your horizontal radius or the minor radius, and b is nothing but your vertical or the major radius. Is everybody with me? Now that being said, if I say, let's say I have an equation for the ellipse which says x square by 16 plus y square by 9 equal to 1. So just by looking at this, you see that this is certainly not an equation for the circle because you have two radiuses that you're talking about. So this looks like an equation of an ellipse. Now here if you have to find out what is the major and minor radius, you will see, okay, this is nothing but 4 square and this is nothing but 3 square. So my minor the major radius is 4, or A is 4, or the radius along the horizontal axis is 4 and radius along the vertical axis is 3. Yeah. So just by looking at this equation, you will be able to determine, and when you see this, right, from this you can make out that, okay, the center of this ellipse is at the origin of the coordinate plane. And if at all you happen to see something like x minus 4 squared plus y minus 3 squared divided by this divided by, let's say, 36, this divided by, let's say, 81 equal to 1. So as soon as you see this, this gives you a clear indication that your the center of this ellipse is not coinciding with, sorry about that, center of your ellipse is not coinciding with the origin. What is the origin here? What you will do is, you will relate that with the same formula, x minus h squared plus y minus k squared equal to r squared. This is a standard form of the circle equation. You will relate that with this, and here this 4, 3 becomes the center of this ellipse. So basically it's like this, and your coordinate plane is somewhere here. I mean, not exactly here, obviously 4, 3, so maybe here. So that is how this is 4 and this is 3. So you know that my origin is, the center of this ellipse is 4, 3. And from this you know that your major radius. So this, now look at this. This is the radius along the x-axis, and this is the radius along the y-axis. Now, can somebody tell me which one is the major axis? Is A the major axis or is B the major axis here? Did you guys get the question first? I'm saying with this equation, when you see x minus 4 squared by 36 plus y minus 3 squared by 81, I'm saying by looking at this equation, which one is your major radius versus which one is your minor radius? Did I get everybody confused? Dave, Prisha, anybody? I mean, it's okay. If I'm getting you guys confused, it's my job to get it clear for you guys. But let me write this equation one more time. I'm just trying to make sure that by looking at the equation, are you able to determine the key things that we need to know about them? Let's say I have x minus 3 squared plus y minus 4 squared divided by 36, this divided by 81 equal to 1. So this is certainly an equation for an ellipse. Just by looking at this equation, if I asked you guys, can you tell me what is the center of this ellipse and what is the major and minor radius of this ellipse? Any thoughts? Yeah, Chris.
The center is 3, 4, right?
Yes. It's, see, x minus h plus y minus k, where h and k is your coordinates for the origin. It again relates to the same standard form of the circle, right? So as you rightly said, it's 3, 4. So you got the center. Now, if let's say if I have to draw this, I know this is my origin of the coordinate plane. It's 3, 4. So if 1, 2, 3, 4, 5, 6, 7, whatever, 2, 3, 4, 5, you know the 3, 4. So you're essentially talking about this being the center of the ellipse. You got the center of the ellipse. Now, I'm saying, tell me what is the major and minor radius of this ellipse? Any thoughts? Prisha, Dhanushri, Dev? Pin drop silence. Chris, any thoughts?
I think it might be like a vertical ellipse, not a horizontal ellipse.
Yes. Yep. Yeah, Prisha.
I'm taking like a wild guess. Would it either be 6 or 9 because of the 36 and 81 in the denominators?
Yeah. So it is. See, this is 6 squared. This is 9 squared. Now, which one is major radius? Obviously, whichever is bigger, right? That's the major radius. Whichever is smaller is the minor radius, right? Now, this one says y minus 4 divided by 9 squared, meaning the length along the y-axis is 9, meaning as Chris was saying, this looks to be a vertical ellipse where this is 9 and then this is 6 squared, or along the horizontal axis the width is 6. Yeah. So by looking at this one, you would be able to determine what would be my center, what would be the minor and major radius of the ellipse. Yeah. Now we also touched upon a very unique property of an ellipse, which is called the foci or the focal points. Meaning, if you have an ellipse, it has a very interesting property. Meaning, this is your, let's say this is your horizontal or major axis, and this is your vertical or minor axis. There are 2 points along the horizontal axis. If you pick up these two, and these 2 points are such that they are symmetric, meaning the distance from here to here and distance from here to here is same. Let's say if this is, I'll not call it A, let me call it K. If this is K, this is also K. And from here to here, if this is, let's say, L, from here to here is also L. That's what I meant by symmetry. Okay. So these 2 points are called foci or the focal points. And the best part of these two, I mean the main property of these 2 focal points is that if you pick up any point on the perimeter, right, be it here, be it here, be it here, be it here, distance from here to here and distance from here to here, meaning any point on the perimeter, if you pick up, take this length and take this length. Basically the distance from the foci, let's say this is D1 and this is D2. D1 plus D2 will always be equal to 2 times the length of the major axis. Major radius basically. Yeah. So this is a unique property of an ellipse, where these 2 points are called focal points or foci. Okay. Which is, and these 2 points are lying along the horizontal axis, and they are both symmetric, meaning they are equidistant from the ends as well as the center, and such that any point you pick up on the perimeter, let's say if I pick up this point, this distance plus this distance, these 2 will be again equal to 2a, 2 times the length. Now there are different ways to prove it. You can, let's say, since this one holds true, I mean if, let's say if I pick up this point, this is also the perimeter, meaning from here to here plus from here to here will be equal to 2a. And that you can see, because this length and this length is same. So this length plus this length will be equal to this length plus this length, which is equal to 2a. This is just one concept that you can use for getting a hang of this particular thing. I mean, this is the easiest way to be assured that any point on the perimeter, the distance of that point with both the foci, if you add them together, that will be 2a, or 2 times the major radius. Any questions? Dhanushri was trying to say something, I believe. Is it clear to everybody? Dev, Prisha, Dhanushri, Chris?
Yes, sir.
Okay. Alright, so now, if you extend this thing a little bit more, meaning, one thing that we realize that, okay, yeah, Dhanushri? Saying something? Your voice is breaking better. Say that again. Okay. So once you are able to speak up, I will wait to hear from you, but let me continue with what I was saying. So this is my ellipse. Even if it doesn't look like ellipse, just bear with my drawing skills. So what we learned is, this is my horizontal on the major axis, this is my vertical or the minor axis. Here to here is my major radius, which I am calling as A. Here to here is my minor radius, which I am calling as B. And again, we know the formula for the ellipse anyways. So with respect to foci, what we understood was, these are 2 points which we can call as foci or the focal points. And the unique behavior is, if you pick up any point on the perimeter, the distance from this to this plus this to this is always equal to 2a. This is a property, and which we saw by picking up one point on the extreme ends, because obviously every point that you try picking up and try solving it, you can do it, but we just took an easier route. We picked up one point on the extreme end and we tried to ascertain that this property holds true. Now let's go a little further. So this, from center to this point, these are called focal points, right? So this distance from here to here, you can also call as focal length. So focal length is nothing but the distance from origin to the foci, either side. So this here to here, or the focal point, is called focal length. So let's represent this as f. Now let's see if we can find out some relationship between f, a and b. Okay. So let's pick up a point on the minor axis, and this is, let's say this point is whatever. Let's say this is point K, and this is, these are foci. I'll call it f1 and I'll call this f2. So if I pick up this point and join these two, what this means is, now if you look at this is a very symmetric shape. What does it mean is, distance from here to here will also be the same. Let's say this is d1, and let's say this here to here is d2. But essentially what it means is, we know from the property of the foci is d1 plus d2 will be equal to 2 times a, which is my major radius. And interestingly, since I am picking up the center point here, and these two foci are symmetric, meaning equidistant from here to here, that means this d1 and d2 will also be the same. Or we can say, instead of saying d1, d2, I will say this is d and this is also d. So 2 times d is 2a, or d equals a. So that means this distance from here to here is nothing but a, or the major radius. Am I confusing anybody successfully so far? Or am I being able to confuse you guys? Are you able to agree to that this length is a? Both the lengths?
Wait, could you clarify that a little bit?
Okay, now, so one property we saw that when you talk with respect to foci, you say that these foci are such an interesting property of an ellipse, such that if you pick up any point on the perimeter of the ellipse, here to here plus here to here together will be 2a. Agreed?
Yeah.
Now, I'm not picking up this point. This point I am not liking it. It's not fun. I'm picking up something that is little easier for me to deal with. So what I did was, I picked up the point here on the minor axis. Hey Dhanashree. Can you hear me okay, Beta?
Sorry,
Can you hear me?
Yeah, I can hear you right now, but there's something wrong with my computer and they just shut off. So
Okay. Alright. So basically I believe you could hear me saying that foci are two symmetric points along the major axis, such that if you pick up any point on the perimeter of the ellipse, the sum of the distance from the foci will be equal to 2a. That part you could hear me, right?
yes, sir.
Okay. Now we are trying to go to the next level and trying to figure out what is the relationship between the foci, or we are calling it focal length, because these are two focal points which we are calling as foci. What is the relationship between this focal length and the other two minor and major radius that we have for ellipse. So we picked up a point here which is on the along the minor axis. Up to that is clear, right, Chris? Dave? Rishabh?
Yeah.
So now, since we know that the foci are symmetric, meaning they are equidistant from here or from the center. Similarly, this meaning this distance and this distance are same. This distance and this distance are same. Yeah. Since I have picked up this point, so going by the property of foci, what we know is this length plus this length together would be equal to 2a, 2 times the major axis. So if I call this distance as d1 and this distance as d2, I am essentially saying that d1 plus d2 equal to 2a. Up to this much is okay?
Yeah.
Now, if you kind of dig little deeper into it, what you see is these two focal points are symmetric. Meaning distance from here to here is same, here to here is same. Or here to here is also same. Yeah. So essentially that would mean, since I am picking up a center point, that means this distance and this distance will also be the same. Is that okay to accept optically?
Yeah.
Yeah. That means I can say my d1 and d2 are same actually. I will not say d1, d2 to create confusion for myself. I will say d plus d. Yeah.
Yeah.
That means 2d equals 2a, which would mean d equals a. So this distance here to here is equal to a. Are you guys able to believe that?
So this is only true when you pick a certain point, correct?
This is true only when I'm picking up a point on the perimeter along the minor axis.
Okay. Yeah.
Yeah?
Yeah.
Prisha, Dev, Dhanushri, are you guys able to believe me?
Yes, sir.
Okay.
Yes, sir.
So now, so that would mean that if I have an ellipse, let me again wipe off everything that I did to confuse you guys and put a clearer picture. So what I was saying so far is, this is my ellipse, this is my major axis, this is my minor axis, and again excuse me for my drawing skills, okay? I wish I could have been a better person when it comes to drawing things, okay? Just manage this. Now, assume this is ellipse, and I'm saying these are my two focal points or foci, okay? And I have picked up a point along the minor axis, and I'm joining these two. And I'm saying here to here is A, here to here is also A, here to here is B, and here to here is B. I'm saying this plus this equals 2A. That means D and this are same. So D equals A. Up to that is okay, right? So that part is clear, right? Okay. Now I'm saying that explore your visualization skills further. Now look at this part alone. What does it look like? This is nothing but a right angle triangle. Agreed? Because these are my two minor and major axes cutting each other at 90 degrees. Yeah? So here to here is something which I am calling as F, or a focal length. That's what we are trying to find out. We see that this is a right angle triangle, and when you're dealing with a right angle triangle, the first thing that comes to our mind is Pythagorean theorem. So this square, meaning F square plus this square, which is nothing but my B, my minor radius, equal to this D square, or I will say A square, because this is what we found here. Yeah?
Yes.
That would mean F square equal to A square minus B square. Agree? Or F will be equal to square root of A square minus B square. So here what do we see? This is the relationship between the major radius and the minor radius, major radius, minor radius, and the focal length. And focal length is nothing but the distance from origin to one of the foci. Yeah. So now, foci, which was sounding more like a magical things, the two interesting points along the horizontal axis, such that it is symmetric, and any point that you pick up around along the perimeter of the ellipse, the distance, sum of the distance from both the foci would be 2a. That has a mathematical representation now, relating to the major and minor radius. Yeah. Is this part clear? Yeah. And trust me, nobody in the class has to say yes if you don't agree to what I'm saying. Okay. So I mean, my only job is to make sure that you guys get the concept right. So if I'm forcing you guys to say yes, you have all the rights to say, sir, I didn't understand. Okay. Don't be shy. That's my request to you. Okay. So up to this much is clear, right? And we'll try not to go into the parabola part of it. The reason being, we have learned parabola in other classes, and we'll have a separate, we'll have separate classes to talk about parabola, because we have dealt with parabola enough, and we will deal with it enough in other classes. When it comes to conic section, our focus would be on primarily on the standard form, the circle equation, because that helps us derive the related equation for ellipse, and also you will see hyperbola. And so ellipse, little bit of circle, and then hyperbola is what we'll cover as part of this unit. However, when we go back to parabola, we'll talk about it separately. That's okay, right? Now, so we looked at the circle equation, we related that with the ellipse, we found what is the major axis, minor axis, major radius, minor radius, and then what is the foci, and then what is the relationship between the foci and the major and minor radius of an ellipse. Yeah. So as part of the syllabus, when you guys deal with it, we have to always keep in mind that there is only one equation, which is my standard form of the circle equation, and that is what we will use for deriving everything else. If you look at circle and ellipse, though we looked at circle equation and then we tried relating that with ellipse, but when you have to find out the relationship between circle and ellipse, I would say ellipse is the father or the parent, and circle is child. Why so? Because ellipse has major and minor radius. If you deal with this, let's say x square by a square plus y square by b square equal to 1. If this is my equation for the ellipse, when the center of the ellipse is coinciding with the origin, I will treat this as the parent for the circle. Why? Because if my a and b becomes the same, meaning my horizontal radius and the vertical radius becomes the same, that is what gives birth to a circle. So this is an ellipse. I will say this is also an ellipse where my major axis, major radius and minor radius are same. And when you put, instead of a square and b square, you should put r square, because both the radiuses are same. This becomes a circle equation, wherein the vice versa may not be true. Yeah. So you'll always look at ellipse as the parent and circle as a derived form of an ellipse. More of a conceptual speech than anything else. But when it comes to deriving the formula, obviously I know that everybody is more comfortable seeing the circle equation, and you can relate that relate with the circle equation to derive all the equation for ellipse and find out the properties and how do you deal with that. Only thing new that we are learning here is foci. And again, if you relate that with circle also, right? Foci would be 2 points. Pick up any point, it will be equal to 2 times a or 2 times radius. Now you pick up this point here, same thing, 2a. You pick up any point here, this and this. will become again, you can relate that with the concept that we've learned with foci. Good thing is in circle scenario we don't deal with foci, but as far as the property is concerned, you can certainly apply that and see if foci holds true in case of circle also or not. Now here, if you put this formula in case of a circle, your A and B are the same. That means f will be equal to 0 and the focal length will be equal to 0. So essentially you're talking about this being your foci because your focal length is 0. So this is the only point which is equidistant from any point. And now let's say you pick up this point. There is only one foci, so you'll probably multiply that 2 times to get 2 times r or 2 times radius. So again, let's not muddle the water. I'm saying we'll look at foci as a concept which is more predominant with respect to ellipse. And if you want to toy around with that, you can always relate that to circle also if you want to. Yeah. Is everybody okay with what I said? Now, and as I said, we will use our circle equation as the base to deal with all things related to the conic section. So now we looked at ellipse, we looked at circle. Now let's look at hyperbola. And when we talk about hyperbola, simple thing that we want to relate to is we have 2 cones sitting on each other's head, and then when you use a plane to cut this is what you get, which is your hyperbola. Now what was our equation for a circle? X squared plus y squared equal to r squared. Here again it's a very it's a very lame approach, but if I kind of force you guys to visualize only for a little bit, if you look at this hyperbola, right, these are 2 pieces or the 2 cells of a broken egg, meaning if you flip them together it will eventually form an ellipse, and at a very high level. Yeah, it will not make a circle for sure. So that is what we take as a base to find out how do I put a structure for a parabola. So our equation for a parabola, my equation for an ellipse is x squared plus y squared by a squared plus y squared by b squared equal to 1. Since we are flipping, see what is happening is, if you are breaking this ellipse and one part goes, let's say if you are looking at hyperbola like this, where you are looking at the mirror image along the x-axis, what you are doing is, you had an ellipse before, you moved half of the part below, and that is how you got 2 pieces of ellipse to make it hyperbola. Correct? Am I making sense? I know I was giving you guys a very, not a very scientific approach, but I'm just trying to help you guys relate this so that when you look at the equation, you'll be able to make some sense out of it. But whatever I've said so far, is it somewhat acceptable, even if it's not convincing? Yeah, Chris?
Yeah, I did.
Okay. So that is why the equation for the hyperbola that we look at would be somewhat closer to the equation that we have seen for ellipse. My equation for the ellipse is this. Now what's happening is, we are saying, let's add another flavor to it. That is how this is split. So what essentially this means is, one part of your hyperbola is going in the negative direction, one is in the positive direction. Wherein, if you look at an ellipse, right, here everything is along the x-axis or along the y-axis, but we are flipping it open, right? That's how it's becoming a hyperbola. So we'll use that as a base to define the standard form of a parabola. Now you'll say, sir, you are forcing us to believe that this is the equation, and I fully agree that I'm kind of right now forcing you guys, but when we go look at the examples, that is when you will see it's making more sense. Yeah. So now if I collate and give you a summarized view of what we have seen so far with respect to circle, parabola and hyperbola, we will have a table with 3 columns. I need a better pen. So let's say this is circle, this is ellipse, and this is hyperbola. Okay. So here we saw my standard form, the equation is x squared plus y squared equal to r squared. Here that changed to x squared x squared by a squared plus y squared by b squared equal to 1. And here I am saying that my equation for the hyperbola would be or it could be y squared by b squared minus x squared by a squared equal to 1. Either of the two. And we'll go deeper into it when we talk in depth about hyperbola. But this is just a going position where I wanted you guys to make sure that just by looking at the equation, are we able to relate to which one is holding true for an ellipse versus a hyperbola versus a circle? Yeah. And again, if you look at A and B, these are nothing but, if you are looking at this hyperbola, right? Your A is your minor, I'll call it minor radius. B I'll call as major radius. Why I'm saying so. A is the radius along the x-axis. B is my radius along the y-axis. And again, by looking at this one, you would not be able to appreciate what do I mean by radius. We'll probably use a different term for this one, but I'm just trying to relate that with what you're seeing here. Okay. So this tells you the width, the symmetric width along the x-axis, which is your A. B is nothing but your symmetric width along the y-axis from the center. And interestingly, the center is here. Hyperbola has its center outside. So basically what's happening is, if you try closing it, it will become shaped like this. So that's why the center is here. But we are looking at it with it being cut open. That's why you are seeing this. That's why this center is, in the case of a hyperbola, you will see that the center is outside the shape, and on every other visual representation that you see, you will be able to relate that with an ellipse. Is that making sense at all or no? Yeah? Okay. So this was just the visual part of it. Now let's look at how do we look at these formulas to make a little more meaningful sense out of it. Now when you're looking at a hyperbola, right? Let's say this is my hyperbola. Essentially, when you imagine these points, where it becomes an asymptote. This is your vertical asymptote. Similarly, if you have a hyperbola like this, these are the points, the end points it becomes your horizontal asymptote, meaning where the value of x, for a certain value of y, the value of x goes towards infinity. Yeah. So basically, we will relate the asymptote concept here also with respect to hyperbola, but just from a visualization point of view, these are your points where it tends towards infinity along the vertical axis, or in this case along the horizontal axis. And by looking at these formulas or the equations, we should be able to determine which one is a horizontal pair of parabolas versus which one is facing upward or downward. So this is like the hyperbola which is facing sideways, and this is where it is facing upward or downward. Okay, and we'll do more mining of these equations in the next class to kind of go deeper into it. But before we do so, is that part so far understandable and digestible? Because if you're not able to digest, then regardless of how far we go, I'll only create confusion. Is everybody with me? Dave, Prisha, Dhanushri, Chris. Okay. Now let's look at some interesting aspect of this equation. Still, for now, I'm saying that this is my standard form of a hyperbola. Okay. And we'll look at a little bit more detail around this one. Now, let's take this equation. So, x squared by a squared minus y squared by b squared equal to 1. So, that would mean x squared minus by a squared equal to 1 plus y squared by b squared. Now, let's multiply everything by a squared. So, this becomes x squared into a squared by a squared equal to 1 into a squared plus y squared into a squared by b squared. These two you can do tic-tac-toe. So this equation becomes x squared equal to a squared plus y squared times a squared by b squared. And you think that what this old man is playing with, right? Now let's play a little bit more. Y squared times a squared by b squared plus a squared. Now if you look at this equation, when I was talking about the asymptote, what do we mean by that? A value of x or y for which the corresponding value goes towards infinity. Or what would be the value of, let's say if I'm looking at y as a value which is tending towards infinity, what will be my corresponding value of x? So if I'm looking at, let's say this and this, so I'm saying what is the value of x here? We know that these are the points where it's going towards the vertical asymptote. So what is the value of my x where y starts tending towards infinity? Or what is the value of y when y is infinity? What is my corresponding value of x? Right? Because up to this point, my value of x is not changing, only y is moving towards infinity. So in this equation, if you see, right, when y is tending towards infinity, you can literally ignore this piece, right? When y is infinity multiplied by something plus a has no relevance when you are comparing any number a number which is, let's say, even 20 billion. This is infinity. If you multiply infinity with something, that is also infinity. And then you are comparing infinity with somebody who has no relevance actually, not much relevance. So essentially what that would mean is when y is infinity, your value of x will be the square root of y squared into a squared by b squared. You can safely ignore this piece. Or you can say my x value will be plus minus y times a by b. And again, here y is moving towards infinity. So these two things, sorry, my bad. So when we are looking at y being infinity, when y is infinity, a by b, meaning your larger radius by smaller radius, which also defines your slope. Basically, if you're looking at this ellipse also, right? This is a larger radius and this is a smaller radius. If you compare this one versus this one or this one, what do you see? Your A to B ratio determines the shape and size of your ellipse, whether it's a horizontal ellipse or a vertical ellipse, right? A by B ratio, right? If A by B is greater than 1, then you know that it's a horizontal ellipse. If A by B is less than 1, then you know it's a vertical ellipse, right? So basically it defines how your ellipse is shaping up. So we'll relate that concept here, and you can, if we call this as a slope of the hyperbola, you see that when y is moving towards infinity, this part is becoming little irrelevant. Okay, and again, the main purpose of this is to understand that there are two parts to the whole hyperbola here, where there is one a by b. In this case, both a and b are here. A is positive, b is positive. In this case, you are seeing that your a is positive but b is negative. So that's why when you see x equals plus minus y times a by b, this clearly indicates, or you can relate it to this equation that when I have a positive slope, meaning a by b is positive, I'm talking about this part. When a by b is negative, or let me put it this way. Let me say a by b equals x by y value plus minus this, right? So here you are looking at, for every value of x and y, your slope has two parts to it. One is the positive value, one is the negative value, and that clearly determines, or that helps you determine that there are two flavors to it. One is along the, one second, you guys got logged out. One part is when it's reflecting along the x-axis or y-axis. One side of it will be positive, one will be negative, and this is just to give you that view that okay, when you are looking at a hyperbola, you are talking about the slope not being consistent always, and there are two flavors to it, and we'll probably dig little deeper into it, and when we talk in detail about all the properties of hyperbola, how do you relate this one, which one will be when you have x value being positive, when you have x value being negative, versus y value being positive or y value being negative. How do you determine whether your hyperbola is this way or anything else? Okay, so for now I will probably not confuse you guys a little more. Okay, I will only tell one thing, that when you look at the equation for hyperbola, we'll again relate that with the circles equation that we have seen. So in case of circle, we knew that we can say x squared plus y squared equal to r squared, or x minus h squared plus y minus k squared equals r squared. Same way, if we relate that with the hyperbola also, we realize that in case of hyperbola, we say x squared by a squared minus y squared by b squared equal to r squared, not r squared, equal to 1. Or we can say x minus h squared by a squared minus y minus k squared by b squared equal to 1. Or we can flip the sign. So whatever is positive here, that we can make negative. Whatever is positive, that becomes negative. So this negative becomes positive, this becomes negative. So there are two flavors of hyperbola equation that we will talk about. And then same thing, this, like here h and k are the coordinates of the center, the same thing applies in case of hyperbola also. So if you have an equation for hyperbola like this, you will be able to determine what is the coordinates of the center, where exactly the hyperbola is going to lie. And we'll do a few problems in the next class as well, so that whatever I've been blabbering so far, we'll see the application of that and relate that with what kind of problems we'll have to deal with as part of the syllabus for us. But towards last 10 minutes of the class, I think I was myself not very clear about what I was trying to convey. That's why, except this part, last 5 minutes of the class you can probably ignore, because that will get clarified when I show you guys more example. Always talking with formula might not help. We'll use this as a base, saying that this is my circle equation, which helps me determine equation for ellipse. If I take out the plus part and put the minus piece into it, that becomes my equation for the hyperbola. And we will deal with more problems in the next class, so that whatever confusion I created today, that will get knocked off. Yeah. But honestly speaking, I mean, we have 3-4 more minutes, but just curious, did I confuse you guys enough, or I was still making a little bit of sense? And be honest, I mean, there's nothing hidden between teacher and the student. That's fine.
Yes.
What does just mean, Dhanusri? Elaborate.
Everything makes sense.
Makes-
I understood everything pretty well.
Oh, okay, that's good. Chris, Dave, Prisha, were you guys able to follow what I was saying?
Yes, sir.
Oh, okay.
Yes, sir.
Okay. So in the next class, I mean, though I had planned to cover the following topics, and let me look at what all we planned and what all we covered. So we had planned to cover introduction to hyperbola, understanding the properties of hyperbola, and analyzing the formula, graphing hyperbola. So I think these two topics we'll cover in the next class, and there's one more, I think. These 3 topics we'll cover in the next class. Primarily it will be around hyperbola, looking at the properties, how do we relate things, and then solve a few problems that will be more relevant to you guys. And once we do that, we'll look at how do we graph the hyperbola also, because graphing would be fairly straightforward. I mean, if you understand this part of the formula, we would be able to figure out where my origin is going to be. Is it a horizontal facing hyperbola, or is it a upward or downward facing hyperbola? Once we determine that, then we should be able to graph it. So this will remain our base for what we are going to learn in the next class, and let's break our head with that. Yeah. All right, I'll let you guys go. Enjoy the rest of your evening.
Thank you, sir.
Hope you guys get some snow day tomorrow.
Thank you, sir.
All right, bye bye. Good night.
Thank you.
Bye bye.
Thank you.
Yeah, bye bye.